this. So, got your test back. The average, because I know you're gonna ask. I know you will. Test 2. Average, I want to say was about 64% there. So not terrible, but not great. And so don't worry, you'll have a chance to redeem yourselves on the final exam where you're going to see it all over again. So I will say this, please check all my tallies. So how I mark is you start at 100 and then I subtract marks. And so the total, unless I'm being sloppy, should be at the bottom of the page and then transferred to that table on the inside of the cover page. Now, I finished these at 1 last night. So I don't think I was very thorough. So I want you to, I did double check the tallies in the table, but I didn't double check the tallies that came from the pages to the table. So I checked the table, and if the table's good and matches what's in your pages, then that's cool. But if it doesn't, just let me know and I'll fix it, and that's fine. But unless it's a lower grade, then don't tell me. Then just ride that high. But so I want you to check those. Okay. And because it was so late, I haven't posted the solutions, but I will after class. And so there were 2 versions again, and I wrote the version number on the top of your page. And I know what else you're wondering. Hey, if there's 2 versions, what else could you be wondering? Was there a significant difference in the averages? What? We're going to do stats on a stats test? Yes, we are. So what's my null hypothesis? Mu of version 1 is the same as mu of version 2. I have to assume that they're the same until I have proof otherwise, which in this case, I'm hoping I don't, because that would be really, really bad, right? Then the averages would be different from each other. My alternative, I use a 2-sided test. I only want to know if there's a difference between the 2. And so mu1 is not equal to mu2. Then what did I do? I don't do the test by hand. I did it in Excel. And I did the t.test function in Excel. And I found the p-value was something like 0.95. Phew. Why phew? There's no significant difference between the 2 averages. And that's a good thing, right? Because if you're putting out 2 versions, you should probably make sure that they are equivalent. And so they are. In fact, this p-value is crazy. So close to 1, right? So I'm not concerned at all. So therefore, there is no significant difference in the grade averages from tests, from version 1 and version 2, I should say. They're the same. Ta-da! Stats in action. Yeah. I usually mark this test harder, but I suspect it's kind of a rough time in the term for you guys, because I don't know. Usually I can mark it a little bit harder. And if you feel like I marked it hard, it's to your benefit. I know, not really. These are my grades. I know that. but I want you to be really, really on top of it for the final exam, right? And so I find that the only way that we learn is if we're kind of penalized a little bit. Okay, nothing crazy. I didn't, take any crazy marks off, but so I wrote little notes. I took marks off unless it's obvious, and then so we can go through those if you'd like, but probably not together as a group. That doesn't really make sense. Okay. Any questions about the test before we get started? Okay. You guys are like parted. How about a little bit of review? In terms of the formula sheet, we actually finished everything on the formula sheet that we're going to see this term. In fact, what I'm toying with is just finishing all of regression this week and then just doing final exam review next week. Okay. And so I'll bring some questions for us to work on and that kind of thing. Okay. We talked about the correlation. We talked briefly about the covariance in the sense that that's one of the things that I could give you in order to calculate the correlation. Now, this is super overwhelming, okay? But the only things that you really need on here, how can I do this, is this formula, that the correlation, and then potentially this note, if that hasn't been ingrained yet, that the correlation is the covariance over the standard deviation of X times the standard deviation of Y. So here, everything else is just kind of, hey, why is it jumping around so much? Everything else is just kind of gravy here. It's for a higher level course where we actually do use it, but for us in this course, I should have removed it. Okay. Where R is the correlation between X and Y. Oops. What were some facts about the correlation? The correlation goes between -1 and 1, right? So R is between -1 and 1. Yeah. A correlation of 0 means that there's no relationship. If R is 0, there's no relationship. Right? Just looks like a random cloud of points. Doesn't matter where you draw the line, there's no anchor there, there's no pattern. If R is -1, there is a perfect negative relationship. Which would look like this, all the points on the exact same line. Of course, moving from no relationship, so a correlation of 0, down to a correlation of -1, right? This cloud is going to kind of straighten out the closer you get to -1. Okay. And then correlation of 1 is a perfect positive relationship. Which looks like this. Let me add a page here. Let's also define S subscript XY. S subscript XY is the covariance of X and Y. We don't need to know anything beyond, if I tell you it had a covariance of this, right, then you know that that's your SXY. Okay. Notice that these are little subscripts. So S subscript X is the standard deviation of your X's, right? And so because in your data set now, to make a scatter plot, you're going to have a column of X's and a column of Y's, and you can calculate the mean and the standard deviation of each of those columns. And so we need some way to denote that. And so this is the standard deviation of X. And then, of course, S subscript Y is the standard deviation of Y. If I can do some shorthand there. Okay, nice. So our goal, right, was to build a regression equation. Now, a regression equation, and instead of writing it out, I'm just going to steal it from your formula sheet so that you can see it, how you'll have it. The least squares regression line is just a line of best fit. And so a line has the form y equals mx plus b, right? And so we use b1 for the slope. And so the slope is b1 because it's attached to the x, and b0 or b0 is the y-intercept. And so I've got them both listed here, right? But ultimately what we're trying to do is we're trying to build this regression line. Okay? Let's remember what the y hat is. Y hat is the predicted value of y. Because our goal, it doesn't look like a y. Our goal, right, is to be able to predict other values of y for unseen values of x, or just general values of x. So now, if you have to build this line, okay, first thing you're going to do is find the slope. Well, the slope takes the correlation, which we just saw. So either I give it to you, right, or because you need SY and SX here, we've already got those if I gave you the covariance, right? And so still only 3 pieces of information so far that you'd need. Okay. You can plug those in, making sure that you're really, really careful with, right, your Y and your X, right? Y is the standard deviation of your response variable. And SX is the standard deviation of your explanatory variable. Okay. If you mix those up and there's a big difference, right? 2/1 is way different from 1/2. And so you can see how that would make a mess of your slope. Okay. And so you want to be really careful before you even start the question and just convince yourself that you know which ones are the Y's and which ones are the X's and what information belongs to which group. Okay. And once you have the slope, then you're going to use it to find the y-intercept. Okay. X bar and Y bar. X bar is the mean of the X's, and Y bar is the mean of the Y's. And so here, where X bar is the mean of X, and of course Y bar is the mean of Y. We talked about the different constructions of finding this line, but I want to introduce one last concept before I summarize it. Okay. We also talked about the residuals. The residual is just exactly as it sounds. It's the leftover part where the points are, or how far the points are from the line. And so it's your observed y minus your predicted y. And how we find the least squares regression line is we minimize those squared residuals, right? And that's what these formulas are doing. So we don't need to worry about how that works in the background, but that is what the formula is doing. Okay. So we had an example where we calculated the slope, where we calculated the intercept, and then we also introduced kind of at the end here, how do we generally interpret the slope? It's one of those where I want you to commit it to memory, maybe if it's not clicking, right? But I will get you to interpret the slope once you've found it. Okay. The general interpretation is for each unit increase in x, we expect a slope increase in the predicted value of y. We expect a slope increase in the predicted value of y. Y hat. You can kind of gather that from the equation. Y hat is the predicted value of y is b naught plus b1 times x. Now, if you let x go from 1 to 2, right, the only thing that would change in your y hat is that it would increase by b1, right? And so you can kind of use the formula that's on your formula sheet to guide your interpretation of the slope, right? Same thing for the intercept. What's the intercept? B0, right? That's going to be your predicted value of y when x is 0. Right? So to interpret the intercept, when I say intercept, I mean the y-intercept. I'll clarify there, but we don't care about the x-intercept. So to interpret the y-intercept, the y-intercept is the predicted value of y when x is 0. A follow-up to that would be, is it meaningful? What that's really asking is, well, does x being 0, does that mean anything to you? Is that useful information, or is it just an anchor for your line, right? And so what we saw, and maybe I'll scroll up here, is that for our example, and we did the interpretation in terms of the question, so I'm going to parking lot that because we worked through that last day. But we did find that the intercept was somewhere here, right, when x is 0. But the thing about lines is lines keep going forever, right? Negative infinity, positive infinity. But regression lines only really work, right, for the data that we built it off of, right? We built it off of x's between 75 and 95 in this case, right? So whenever we use the line, it is our best guess, but it's not very reliable, right? If you think about kind of an obvious example, like if you take children's heights with respect to their age, right? As they grow, right? 1 year old through, I don't know, when do you stop growing? 10 years old, maybe you have this kind of linear relationship. You just grow and you grow and you grow and you grow. But if we kept using that line, I would be probably predicted to be 9 feet tall by now, maybe 10 feet tall. which tells you more about my age than anything else, right? And so, and that's not how heights work. We understand that. So we wouldn't use the line to predict outside kind of our growing ages, but we don't always have that built-in knowledge about the data, right? Most of the time, if we're analyzing data, we don't really know what it is, and it doesn't matter, right? Because the analyses are the same, right? So it's kind of this faceless thing. So that's why we have to be really careful about extrapolation. Okay. And so here, usually I do a follow-up, but I'm trying to keep it on the same page. Is it meaningful? What I want you to do is argue whether x equals 0 is useful information, right? Or the predicted value of y when x is 0. Or can x be 0 reasonably? Is really what that follow-up is saying, right? Often the y-intercept is an extrapolation. And then in those cases, I would say it's not very useful, right? But this is one of those where you get to awaken your inner lawyer and just argue however you feel and convince me. And if I'm convinced, then that's cool, right? If you tell me that, yep, knowing what the percentage in poverty of a state with a 0% high school grad rate is, that's meaningful information to me. Okay, right? As long as you center it around x being 0 and that being useful information. So I've got some, well, any questions before we start? Pick up here on Tuesday. Now it's Tuesday. No. Okay, so I'll do a little end of review there. On today. Here we go. So kind of some fun examples of extrapolation. Well, this one isn't that juicy, I guess. We've got the men's age at first marriage over years, but a long time ago, obviously, 1900 to 1975. And so here, between the years just before 1900 to just before 1950, gee, I wonder what happened then. I don't know, maybe a world war or something. Right, some knowledge, right? But we've got this beautiful linear relationship, and we could use that to model all the men's ages at the first marriage. But what would we find? It would probably be before birth if we use this line now, right? That's not very useful. That's, I mean, in theory, I guess, if they're, anyways, no, let's not go down that rabbit hole. But the problem becomes this section, so this kind of green section of the data, or years, right? By kind of probably somewhere around here to probably somewhere around here, right? We should be using a different model. Yeah. And so if we use this blue line to make predictions for these year ranges, right, which we did not use to build the model, we used the blue dots to build the model, right? Then we would get kind of a pretty good prediction here, right, as we're kind of tapering off. And then just by fluke, for those couple of years there, we would have a reasonable estimate. However, or prediction, right? Estimates and predictions are the same thing. However, for the rest of the time here, we should probably be using some sort of non-linear model, which is beyond the scope of this course. They exist, but most of the time what we can do is we can just transform the data and make it a linear model. That's easy. And then you're back to where we are working now. But again, that's kind of for a second or even a third course if you're so inclined. And then for these guys, for the remaining years, this looks relatively linear, right? Not great because it's got a little bit of curvature, but if we kind of put our blinders on, we can fit a linear model for that data. But again, it's not going to be useful for predictions for years earlier than 1975-ish. This one, kind of baffling. I'll move this. BBC News, tisk, tisk, tisk. Women may outsprint men by 2156. Very interesting, and also kind of far off still. So here's the data that they're using. Okay. So we've got the winning times in seconds. That's my pointer. The winning time in seconds, and I guess I have to assume that the blue is, yeah, surprise, surprise, is for the men and the red is for the women. All right, fair enough. So we've got these linear regression lines for each of them, but we only have data up to, looks like about 2012, right? So any predictions outside of 2012 are going to be unreliable. Now, what do you think these dashed lines are? Confidence bounds making an appearance. Okay. So there's going to be spread around this line. We're not going to tackle it, but to know it exists is good enough for me, right? And so to know that we could build confidence bounds, they're called prediction intervals, and we're not, like I said, we're not going to get into it. They're basically confidence intervals around each point on the line. Yeah.
What's R squared?
Haha, nice segue, because I think it might be, haha, thank you. It was almost perfect. What is R squared? So R squared is going to be your correlation squared. Okay. If you take a value between -1 and 1 and you square it, what happens to those negative values? They're going to get folded over, and they're going to, now R squared is going to be between 0 and 1, which is a percentage. Okay. And so what we do is we use this R squared to communicate how well our line fits our data. Okay. And the higher the R squared, the better the line is, right? And so if you're building lots of models, which is usually how we would do it, is you would build a model, you have an idea, okay, I'm going to build a model, and then you say, oh, well, what if I tried doing this instead, right? Pull out some outliers or something like that. And then what you would do is you would compare the R squared at each step. The higher the R squared, the better the line fits your data, right? Or the closer your points are to the line. And so in this case, they're, kind of similar, but the R squared for man is a little bit better. And what that looks like, let me zoom in a lot, is that the points are just closer to the line than the red dots are to the line. All right. So let me move this up here because otherwise I get confused. So the strength of the fit of a linear model is evaluated using R squared. Okay. And so here, I'll just outline that R is the correlation, and it's between -1 and 1. Now, if I square it, r squared is going to be between 0 and 1. Anything between 0 and 1, right, can be rewritten as a percentage. Right? Now it's a proportion or a percentage. A percentage or a proportion. And for some reason, when we square it, it tends to become a capital R squared. But I'll make a note here. Note that R squared is R squared, just like, and R is capital R. So that means that we could reverse it. Go to hairs. What could you do? Then the correlation is going to be the square root of r squared. But when I take the square root, what do I need to do? I need to tack on the plus minus. Okay. So the third and final way that I could give you the correlation would be if I gave you the r squared. Right? And so I'll say and final, just so you don't keep looking. The third way I could give you r is if I give you r squared, I would also need to tell you the direction of the relationship, which is usually if I show you the scatter plot. Okay? Because why would you need the direction of the relationship? R is the strength and direction of a linear relationship. And so if it's a negative relationship, that's when you tack on this negative. And if it's positive, then you leave it positive, right? And the scatter plot. Right? So if you have something that looks like this, a negative relationship here, then r would be the negative square root of r squared. I'm just running out of room here. There. From the negative relationship, oops, versus if I give you and show you that it's a positive relationship, then in that case, r is just the positive square root of r. Kind of sneaky. Right? Or if I'm nice, then I give you the correlation, right? And then I'll ask you to find r squared. But in order to ask you to find what r squared is, we need to know what r squared is, right? And so it is the square of the correlation. So you know mathematically how to find it, right? And we usually report it as a percentage, although I'm not too picky about that at that point. Okay. But it tells us the percent of variability in the response variable explained by the model. And I'm going to give you a little blurb to memorize. But the remainder of the variability, need my pointer. The remainder of the variability, so everything that's left over from R squared, right, and 1, is explained by variables that are not included in the model and just randomness in general, right? We don't expect things to fall on a perfect line. So for our model, we had a correlation of negative 0.62, so we can find the R squared by squaring it. Now, squares of small values behave in a weird way, so use your calculator, right? Because the R squared is 0.38, which is not very good. Okay, but I want to add a page here. So R squared is the percentage of variability in Y explained by the least squares regression line on X. That's a big blurb to read, especially in the final exam, which is the first time that you'll be tested on this stuff, right? And so what I want you to do is have a built-in trigger for when you see something like percentage of variability, right? A percentage is a proportion. So this could say, or proportion of variability. But as soon as you see kind of a long blurb with some hint of percentage or proportion of variability, your brain is going to think R squared, right? Whether I say 78% of the variability in whatever the Y is explained by the least squares regression line on whatever the X is, right? That's how I would give you the R squared. R squared is percent in Y. Yeah. But you would have to fill in what these values are from the question. I feel like I could probably sneak that on to here. Let's do this one because I don't love how she words things. I like to be kind of consistent with my own wording. So R was negative 0.62, right? The correlation we were given was negative 0.62. Checks out, right? I have this negative relationship. And I'll say that this is what we were given. So the question could look something like this. So there are two options. For questions about R squared. Option 1 is I introduce it early, right? And I ask you to find the correlation, right? Or, let's remove this then. This is not given yet. Option 1, introduce it early and ask you, to calculate or to find the correlation. example, let's see here, what was it? 38% of the variability in percentage in poverty, right? The Y, the variability in Y, is explained by the least squares regression line, which is just the line of best fit. Least squares regression line on percentage of high school grads, right? Also given scatter plot. So you'd have the scatter plot, and I give you the scatter plot. I ask you to describe the relationship, the strength, the direction, and the shape of the relationship, right? All three things you need to talk about. And then I would say, part B, 38% of the variability in the percentage in poverty, which is your Y, right, is explained by the least squares regression line on the percentage of high school grads, which is your X in this case. So then, first things first, we only do math not on percentages, but on proportions, right? And so let's start there. So then R squared is 0.38. Right. So R is the square root of 0.38 plus minus the square root of 0.38. See here, should be 0.62, hopefully, but we'll try it. Square root of 0.38 is 0.61644, but let's just say for simplicity, it's plus minus 0.62. Since we see a negative relationship, R is negative 0.62. And then you would have that R to find the slope, right? Because you need to have R some way. Now you have R to find the slope. Okay. So that's one way that I could give you the correlation. Okay. And then add that to the other first two options, right? Where I give you the covariance and the standard deviation of X and the standard deviation of Y, and then you can find R, or I'm nice and I just give it to you, right? But if I'm nice and I just give it to you, that's going to be option 2, right? Is towards the end of the question, right? I would, so option 2, towards the end of the question, right? Given the correlation, right, in the question earlier on, find R squared. It's the color scheme here. For example, what proportion or percentage, right? But I want you to see both. What percentage or proportion of variability, and it's going to be a long blurb, right? But as soon as you see kind of, oh, okay, percentage or proportion of variability, then you can stop reading and then just kind of think R squared and then keep going to confirm. Okay, what proportion of variability in percentage in poverty? That's your Y. Is explained by the least squares regression line. On percentage of high school grads, which is your X. All right, but it's going to have the variable names in there. And that's what makes it so boggy. Another thing that makes it boggy is calling the line of best fit the least squares regression line. That's just being proper, right? You can kind of ignore that. You can just say the line if you want. But you have to read these questions and figure out what it is that's wanted of you. So those are the two options for the R squared question, right? Either at the beginning, then you need to use it to find R, or at the end where I ask you to find R squared. Okay? So then if we're given the correlation is negative 0.62, what color did I use? Then R squared is R squared, which is negative 0.62 squared, 0.38 or 38%. Hopefully, kind of rounding and stuff, but that's okay. Just stealing the numbers from before. Clarify that negative. Nice. Okay. One thing to note is that R, so the correlation and R squared only work for linear models, right? And so if you have a nonlinear model, you can do that, but you're going to need to use other mechanisms, okay, which we don't introduce here, but just so you're aware, I'll make a note here. Note R and R squared only apply to linear models. But like a lot of things, these are kind of traps because you can always calculate these things, right? Just like we can always calculate the average, we can always calculate the standard deviation, but whether they're appropriate or not, that's our job to know. And so just keep in mind that the correlation, especially in R squared, only apply to linear models. And there it is again. What if we have, what if the explanatory variable is categorical? So far we've had a numerical response variable and a numerical categorical, or a numerical explanatory variable, right? And in this course, Y is always numerical. We can, absolutely, we can model categorical response variables, but that's not for us to do, right? And so here, the explanatory variable is your X, right? So the X can be numerical or categorical. What happens when we have a categorical variable? So what if we want to talk about the percentage in poverty versus two regions, right? The region is categorical. With two categories, East and West. of some state, I assume. Or maybe the United States. I don't know. We can fit this model. Yeah. We're still predicting the percentage in poverty, right? But now what's going to happen is this West is what we call a dummy variable. Okay? And so it's just a placeholder for a 0-1 situation. Okay? And there really should be a lot more space here because I need it. Maybe I'll add a page here. How can I copy? So if the region has two categories, East and West, in this model, if West, let West be 1, right? We have these kind of dummy variables. So dummy variables are only 0-1, kind of on-off switches. So if West is on, then East must be off, right? It can only be one of these two categories. It can't be both. Okay? So then East is 0, technically. But we don't even need East as 0 because what are we going to do instead? We're going to say, okay, let's take it back a little bit. Copy this. What if I let West be 0? Let West be 0, then that must be the East region is on, right? If West is off, then the East is on. So if I plug in West equals 0 into this, then I get the predicted percentage in, I'll clean that up, in poverty is 11.17 plus 0.38 times 0. But that's just 11.17. So if the West is off, then we know it's implied that the East is on. And so this is the predicted percentage in poverty for the East region. Therefore, the predicted percent in poverty for the East region is 11.17%, because it's percentage in poverty. So even though we don't have the East in there, we call the East the reference level, right? Because that's your starting point. Okay, so now all these are, or the West is really relative to the starting point of the East. And so we call the East category the reference level. Because now, what if I turn on the West, that it's implied that the East is off? So what if I let the West be 1. Haha, when the West is 1. That means the East region is off. Then I have the predicted poverty is 11.17 plus 0.38 times 1 now. So the West region has a higher predicted percentage in poverty by 0.38 because 0.38 times 1 is just 0.38. So 11.17, plus 0.3, oh, nice try, Emily. 11.17 plus 0.38. Okay. I get 11.55, but I feel like I slipped up still, but just check that. So the predicted percentage in poverty in the West region is 11.55 or 0.38 higher than the East. Right? And so therefore, the predicted percent in poverty, I'll try to keep it on the same page here. In the West is 11.55% or 0.38% more than the East, right? Because the East is the reference level, and then all the other components are just relative to the reference level. So now we can talk about the reference level, right? The reference level is always going to be the category that's missing, right? So that's going to be your jumping off point. And then the additional levels are relative to the reference level. Now the intercept is the estimated average poverty percentage in the eastern states, which is what we found, right? And that is in the eastern states is when West is 0. The slope is the average poverty percentage in Western states, right, is 0.38 because it can only go between 0 and 1, right? 1 unit increase. And so that's if we plug in a 1 for the West, right? We get 11.55. So that's kind of fun. They're little cuties, right? Zeros and ones, just little dummy variables. What if we have 4 regions? We would use, so at this point, we're not going to do calculations by hand anymore. Of course, we would use Excel to generate something like this. Okay. Now, what Excel is going to give you is it's going to give you the intercept, right? Just like we had before, which is essentially a placeholder for the reference level, right? Everything is relative to the intercept. I guess I gave it away. But if we have the Midwest, the West, and the South, then from this list, what am I missing? I have the South on here, I have the West on here, I have the Midwest on here, and I'm missing the Northeast. And so the Northeast must be that 4th region that is the intercept. The intercept or the reference level. So what does that mean? We can rewrite this model using these estimates for the coefficients. So these estimates are coefficients. we can rewrite this model just like we had before. Oops. Poverty hat is 9.50 plus 0.03 times the Midwest. Can I just say mid? And not like in a cool way. Plus 1.79 times the West. Plus 1.79 times the West. Plus 4.16 times the South. So you take these coefficients and you can build the model like this. What if you had to predict the percentage in poverty in the West? I'll do an example. Predict the percent in poverty in the West. Can only be in one of these regions, right? The West. So what does that mean? That means that, okay, this intercept is unaffected, right? That's our reference level. And so all the other ones are relative to the reference level, right? But if it's the West, then the mid is off, right? So it's 0. And the South is off, so it's also 0, right? Multiply by 0, these go away. So then I get the predicted poverty is 9.50 plus 0.03 times 0 plus 1.79 times the West is on, so it gets a 1, plus 4.16 times the South, which is a 0, which is off. So it boils down to a relatively nice formula, right? 9.5 plus 1.79. I get 11.29% in the West. What do all these being positive mean? It would mean that the Northeast has the lowest level, right? And all the other ones you would add a little bit, right? Depending on which region. Yeah. Kind of fun. I'll move this so we can have it all on one screen. Which region has the lowest poverty percentage? Well, I guess I just said it. The lowest has to be the Northeast because all these other ones are adding to it, right? Making it higher and higher, okay? The only time that it's this low is if the West is off, or sorry, the Midwest is off, the West is off, and the South is off, leaving you with the Northeast at 9.5. And I know what you're thinking. These look kind of familiar, right? It's part of our output. And they are the standard error of our estimate. We can get a t-value, right? Which is your estimate minus your hypothesized value, right? How far is it from some hypothesized value divided by the standard error of the estimate? You can try 9.5 relative to what? It's going to be relative to 0. All these things are going to be, how are they relative to 0? So that's nice. So it'll just be 1.79 divided by 1.13 should be 1.59. Let me try it. 1.79 divided by 1.13. Phew. rounding gets weird. I get 1.58, but it has more decimal places behind the scenes. So, but I don't want to make a note about that yet. Or maybe I do. So here, let's do this. This t and this p value, we know how t's behave, right? And we know p values. Okay. So what we really need, or what I need to tell you, is what your null and alternative hypotheses are for these. Okay. And so your null hypothesis is that beta for the south is 0. Remember, beta is the parameter that we use for these coefficients. And then the alternative is that beta for the south is not equal to 0. So it's a two-sided test. It gives you the t. T is always the estimate minus the hypothesized value, which in this case is 0, divided by the standard error of the estimate, which means t would be 4.16 divided by minus 0 divided by 1.07. And t should be roughly 3.87, which is the same there. A t of 3.87 is quite large, and so we know we're going to have a small p-value, and it tells us that this is the two-sided p-value. We're always going to do a two-sided test for these coefficients. But what does that tell me? This is essentially a slope, right? The slope for the south. When I get a significant p-value, so significant p-values is when it's small and you reject h naught, then you have a significant p-value. A significant, I'll put it here, a significant p-value, p-value less than the alpha level, which is really just if we reject h naught, tells me that that predictor is contributing to the model. The predictor is contributing to the model. In fact, it's the only one that's contributing to the model in this case. Does that mean that we would remove these two? No, right? It just means that this little guy is big, and you need them in there to balance things out. You need the other regions, whereas if they are part of a multiple regression where they're not just from one variable, but instead we introduce multiple things like maybe the region and the percentage of high school grads. Right now I have two variables of x that I'm putting in there. That's a multiple regression. So then I would be able to say, okay, I need to keep that one in there, or I can remove it if it's not contributing to the model. But I'm getting ahead of myself. Any questions though, before we talk about outliers briefly? So there's a couple of different types of outliers. I'm not going to, I can't put this little guy anywhere. Everything's getting covered. I'm not going to test you on the different types of outliers, but it is on an assignment. And so it's worth kind of talking about. Where can I put this here? So if we look at something like this, right, the line would fit better, right? If we ignore these outliers, then I would probably be able to fit something a little bit better like this, right? It would change the slope specifically, but also the intercept. But the intercept is just an anchor, and so we don't really care about the intercept that much. But it would change the slope, right? And so removing the outliers, these guys here, would likely change the slope, which in turn would change your predictions. And so it would alter things, kind of, hate to say significantly, right? But one of the problems with outliers is there's no hard and fast rule for how to deal with them, okay? And so when I was in grad school, all the fun people were in biology, and so I hung out with those guys a lot. And so what they would do is they would just delete all their outliers. Outlier, 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 and I was horrified because we shouldn't do that. You can't just delete outliers. They might be telling you something interesting. And so don't do that. But it is common practice in some fields. But just know you shouldn't do it. Okay? You can put them to the side, right? Or what would you do? Ideally, what would you do? If you have this type of situation, you're looking at this is your data, your big research project, your PhD thesis is on the line. What are you going to do? These are outliers, right? They're impacting your line. And so what I would suggest that you do is you could remove them incrementally. You could remove them one by one, right? Remove this little guy, see what the change in the slope is, right? If it's not that big of a deal, then, you know, you can make a decision, right? And that's where the tricky part is. There's no hard and fast rule for the decision that you're going to make, right? But what you're going to do is you're going to compare the slope as you remove these outliers slowly. Or what you could do is you could remove all of them, put them to the side, maybe analyze them separately, right? And then slowly add them back in. And if there's no change to the line, you could keep them in there. But if there's a drastic change to the slope of the line, which would also impact your predictions, then I would probably say exclude the outliers, right? If they're going to change your predictions and make them less reliable, then you should exclude the outliers. Yeah? But it's really just a judgment call, and that's what's no fun about outliers. Yeah? And maybe I'll write here. We can fit the line. Now, the reason I'm being all kind of lackadaisical about fitting the line is because you're just going to use Excel to do it. And it's a matter of, click, 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 and then you've got the line. You could remove a data point, click, 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 you've got a new line, right? And new estimates. And so it's really quite simple to do. And so you can fit the line in Excel or whatever software you're using, probably R at this point, if you're actually doing analyses in your thesis or whatever. But we can fit the line with the outlier, so potentially more than one, and make note of the slope. I'll say and make note of the slope. Then fit the line without. And compare the slope to the old slope. If there is, I usually don't use the word significant, right? Because significant implies a hypothesis test, right? And you can do one, and so that's why I'm comfortable saying it. But if there is a significant difference, we usually remove the outliers. Potentially more than one. And there are names for the different types of outliers. And so here, this would just be a cloud, right? If we just zoom in here, is there any reason why this line should be where it is? I feel like I could have just as well drawn a line with the zero slope, and it would give me just about as good of a prediction, right? I can plug in a value of x and I can calculate the predicted value of y, and there's no relationship here, right? The only reason that I have this strong line is because of this one outlier here. So I'm trying to remember, it's a high leverage point, kind of physics at play, right? Kind of leveraging the line. Doesn't, like I said, I'm not going to test you on the terminology. It just, they exist, so it's nice to talk about them. And so high leverage points that actually influence the slope of the regression line are called influential points. So an example of a non-influential point would be if you had something, an outlier out here, right? It could leverage the line, but if the line's going to try to incorporate it like that, right, it doesn't really change what the slope of the line would have been anyways. So that's the only difference. For a lot of these kind of biology, physics, we take the log. Physics especially, we do log base 10. Now that's a transformation, okay? And so, but what we can do, the reason we do this transformation, this is a transformed y. We took the log of the y's, okay? And so that's a transformation, but the reason we did it is because otherwise we would have this kind of exponential function, which is hard to graph, but straight lines are easy. And the mechanisms for finding the slope and the intercept of straight lines is relatively easy. And so if I transform the y into something that's straight, then that's easier to model. Yeah. And this is a transformed x. And there's lots of different transformations that you can do. But what I find is that each field has their go-to transformation. So for example, physics would use log base 10 because light and things are base 10. And in biology, use log base E, right? The natural log. Often there are other transformations, but we're not going to care about those. Oh, and these ones. Okay. Which of the below best describes the outlier? Let's have a look here. So we've got it outside kind of the cluster here, but I would say it doesn't really influence the line, right? It kind of falls in line with the line. So it is high leverage, but not influential. Okay, I had to check the because it's in line with the rest. Solutions. What if you had to look at something like this? So now our outlier, of course, is this little guy down here. But if you had to take a stab at it, does it look like the slope is affected that much by this outlier? Not really, right? And that there is no follow-up here. It's like, oh yeah, what's the follow-up? Nope, just not much. And so I'll follow it up with, in that case, you're better off just keeping the outliers. You always want to err on the side of keeping as much data as possible. So in this case, I personally, I would keep the outlier in my data. Right, because it doesn't change the slope or my predictions that much, right? And so we always try to keep as much data as possible. We always try to keep as much data as possible. When would it come into play? Outliers affect the mean, right? It wouldn't affect the mean of X because your X's, they're all in the realm here. And so your X's, the mean of the X's is unaffected by this outlier, but the mean of the Y's is affected, right? And so that's going to come into play with with the intercept, I guess, but also in the standard deviation of the Y's, right? The spread of the Y's is affected by this one outlier, but those are all baked into the slope, right? And the intercept. And so if the overall line is unchanged, then we're not too concerned about it. Oh, I can't read all those. Well, it was none of the above. Which of the following is true? None of the above. Let's see here. Influential points always change the intercept of the regression line. That's not true, but also, do we care? I don't care. I'm not going to test you on it. So it's okay. We don't need to go this hard. No. What I do want to talk about is inference for linear regression. We already saw it, right? Just briefly in that output. So I want to show you properly. Okay, so the genetic determination of differences in intelligence. Only in the 1960s could you do something like this. So a study of monozygotic twins reared apart. The data consists of IQ scores for, we assume it was a random sample of 27 identical twins, although that seems unlikely. One was raised by foster parents and the other by the biological parents. Seems cruel and unusual, but we've got the data, so let's use it. So we've got the biological IQ and the foster IQ of the twins. Now this is paired data, right? We can pair these potentially, but we do see that there's a strong positive linear relationship. In fact, the correlation is 0.882. Now, Excel makes slightly nicer output. So this is our output, but Excel looks similar. Okay. So we're going to have the intercept and the x, right? So how you're going to read this, this is your x. This is the estimate of the intercept. Okay. This is the estimate of the coefficient of the slope, or of the x, which is the slope. So here, this is the slope, and this is the intercept. We'll get to these points soon enough. Okay. There's a bunch of gibberish, blah, 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 blah. The only thing we really care about here is r squared. There's two options. They'll be relatively similar, but for now, we'll just use the multiple r squared, but it doesn't really matter which one you use. Later, if you have multiple linear regression, you would use the adjusted r squared, but notice they're the same. So this, what color can I use here? Green, maybe, is your r squared. So we can build our line from here. We were predicting our y, which is our Foster IQ, right? Remembering that this is your y and this is your x, which is why the bio IQ is down here, right, as your x. And so we're predicting y, the Foster IQ. Foster IQ hat. So the predicted Foster IQ from here, the output is 9.20760 plus the slope 0.90144 times x, or if we want to replace it with the bio IQ, which is your x. So you can take this information and generate your least squares regression line. That's nice. Means you don't have to calculate the slope and the intercept. Now it's really a matter of interpreting the slope and interpreting the intercept and using it to predict values, which is really what we would do in kind of real life. So, which of the following is false? An additional 10 points in the biological twins IQ is associated with an additional 9 points in the Foster twins IQ on average. So if this is 10, if the bio IQ is 10 times 0.9 is roughly 9, right? And so this would be true. Let's see here. How about this? I'm going to tell you that this is false, but instead, what I want you to do is I want you to interpret the R squared. Instead of using that weird interpretation or the wrong interpretation, let's just interpret it properly. So we're going to round to 78%, right? 0.7779. So 78% of the variability in Y in Y, which is the Foster IQ, is explained by the least squares regression line on bio IQ, which is not what this blurb is saying, but I don't like it when they do that. And then we already built the linear model by looking at this output. And this is what I wanted to get to, so that's why I'm rushing through it a little bit. Testing for the slope. So assuming that these 27 twins comprise a representative sample of all twins separated at birth, okay, might be a stretch, might not be. We would like to test if these data provide convincing evidence that the IQ of the biological twin is a significant predictor of IQ of the foster twin. And so for it to be a significant predictor, we want to know if the slope attached to the bio IQ is significantly different from 0, right? And so first things first, A is out and C is out. Why? Because they're about B0 and B1. Those are just the estimates from your data, right? We don't want to hypothesize about the data. We know everything about the data. And so, Ned, need to be about beta. Either beta naught here or beta 1. Now, beta naught is the intercept. We can hypothesize about the intercept, and you see that there's a p-value associated with it, but it's not ever interesting because knowing if the intercept is 0 or not it doesn't tell us anything. And so here we rarely care about the intercept. We need it, but just like we've been saying, it's just an anchor for your line, right? So it doesn't really contribute anything, or rarely. Which tells me that it has to be this one here. We want to know if the slope is significantly different from 0, which is what we already established. So if this is the output that we have, this is where I should have written it. I squeezed it onto the slide way before. But this, let's see, what color can I use here? This is your B1. That's the estimate for the slope. This is the standard error of B1. And what we said already is that T is B1 minus 0, right? Because we want to test if the beta 1 is 0 or if beta 1 is significantly different from 0. So that's where the 0 came from, right? How far is my slope from 0? I'm hoping it's far enough away from 0, because what does a slope of 0 mean? All right, let's take it way back. A slope of 0, or let's call it slope, means that there's no relationship between x and y. So you have to assume that there's no relationship until you have proof otherwise. So t, that's one we're working on here, is going to be the estimate for the slope. How far is it from 0, right? Divided by the standard error of B1, which is what we've been doing when we've been doing the square roots of the standard deviations and things like that. Those are the standard errors. But then also we get this p-value. P-value associated with t. So if I have the p-value is very small, right, then same conclusion applies. Since my p-value is approximately 0, it'll never be 0, right, but it's approximately 0. It's less than my alpha level of 0.05, or my assumed alpha level of 0.05, which means I have enough evidence to reject H0 in favor of HA and conclude that the slope is significantly different from 0, making it a contributing predictor of the Foster IQ. Right. So in terms of our conclusion here, it has the same shape as all our other conclusions, right? Since our p-value is approximately 0, don't want to say 0, it's approximately 0. It is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H0. If you're rejecting it, should say in favor of what? In favor of HA, which means the slope is significantly different from 0, which in turn means that bio IQ is a significant predictor of Foster IQ. Therefore, bio IQ is a significant predictor. Can I do this maybe? Of Foster IQ. Right? It helps me predict the Foster IQ. The rest is just a summary of exactly what we did. And let me just see here. Oh, build confidence intervals. Okay, so we've got a little bit. I'll leave it. Pick up here on Thursday. With that, I release you. If you haven't grabbed your test, come grab your test. And if you want a blank one, you can grab a blank one. And I'll see you on Thursday.